Okay, ladies and gentlemen, welcome back. Today what we're going to be discussing is going to be transformations of functions. Now, what you see here are some of the basic functions that we've discussed in previous lessons. The linear function, the quadratic function, cube root, cube, square, the absolute value function. So what we're going to be doing is taking these basic functions and identifying how we're going to transform them, meaning how do they change from what the parent function gives us to something else, where it's been moved, slided horizontally or vertically, stretched, flipped, something like that. Now, generally speaking, the equation that you see here in the middle is pretty much how all functions are transformed. Every function that we have will follow some kind of pattern like this, where we have something a times the function, in parentheses x minus something with the function, and then plus k something with the function. Well, what we see here, everything inside of the parentheses is going to have some kind of a horizontal effect, meaning that's what causes it to slide left to right. Everything on the outside is going to have some kind of a vertical effect. Okay, the A, we'll talk about it in a little bit more detail here in a minute, that will cause a function to either stretch or compress vertically, where the K will cause it to translate. It slides up or down vertically. So basically, every function that we have is going to follow this basic pattern. So that way all of the transformations that we look at follow the same basic pattern. It doesn't really change. So if we have a function written in this form, it's really easy to be able to change it. Now here, make sure you get all this stuff copied down in your notes because it's really, really important, especially when you're, trying to re-educate yourself, relearn this if it's been a little while since you've done it since Algebra 2. But anything inside of the parentheses kind of does opposite of what it says to do. Um, and everything outside of the parentheses pretty much does exactly what it says to do. So here, when we take a look at it, this is kind of where it's explaining it a little bit more. Insiders lie. There's actually stuff that we do inside of the parentheses that behaves counterintuitive to what we think it would be. So basically, inside of the parentheses, it says x minus h. Well, if it says, let's say for instance, it says x minus 5. Well, insiders lie. That says move 5 spaces right. The minus 5 makes you think that, well, we're going to go 5 spaces to the left. But no, the insiders lie. We go the opposite of what it says to do. So if it said x plus 3, that would move us 3 spaces to the left. So that's what they kind of mean by insiders lie. Now there's actually another operation inside of the parentheses here that could stretch or shrink or even reflect horizontally, but we're not going to be getting into it. The primary transformations that we're going to be looking at are the ones that we saw on the previous screen, where we either stretch it or compress it vertically with the A value, move it side to side, or move it up and down with the H or the K value. Okay. So here where it says K, well, that basically says do exactly what it says to do. So say for instance, if we had x minus h plus 3. Well, that says exactly what it means to do. It says move up 3 spaces. Move up 3 spaces. If I said x minus something minus 2, well, that minus 2 says exactly what you think it means. It says move down 2 spaces. So that's what the transformation K is going to basically tell you to do. It translates it up or down, and that's it. Now here the A transformation says it'll actually do 2 things for us. If a is a negative number, it will cause it to reflect over the x-axis. And what we're seeing here is that if a is a fraction between 0 and 1, that would cause it to compress, meaning that maybe where before it looked kind of something like this, and now it kind of looks something like this, where it literally just kind of squishes it down some. And so here the next one is where we're talking about if a is less than 1, meaning that it's negative, that's what causes it to reflect across the x-axis. Now again, make sure you're pausing the video as necessary to get the notes copied down. And let's take a look at our first one here. I didn't do a very good job of putting this one together, but this is the absolute value parent function. That's what you see here in red, meaning that this is what you would get if you said y is equal to the absolute value of x. This is the graph in red would be exactly what you see. Well, what we're doing, according to the transformation that we see, we have f of x is equal to x plus 3. Well, that x plus 3, what we're looking at inside here, that says transform that function. Remember, the insiders lie though, so where it says x plus 3, what we're really going to do is we're going to move this function 3 spaces left. So everything that we have here, we're going to take it and we're going to go 1, 2, 3 spaces to the left. And so that is where our vertex is located at now, is at -3 and 0, rather than the origin. Now to the left and to the right, both of those really just have a slope of like either a +1 or a -1. So we just kind of follow that same thing. And let me see if I can freehand this here. So it's going to come down here and then go up through all of those. And because it's continuous in both directions, our transformed function is still continuous in both directions. So, and it doesn't really matter what the function is. Here it's an absolute value. We could have done the same thing with a linear function, a quadratic function. It doesn't really matter. We still would have done the exact same thing. Move it 3 spaces to the left. So now let's take a look at this one here. This is a square root function. And what you see graphed out for you here is, and it should kind of be continuous, this is what the square root parent function looks like, which would just be y is equal to the square root of x. If we type that into a graphing calculator or made a table of values, the graph that we see on the table is exactly what we would, wind up with. Well, here, what that -5 is telling you to do, that -5 is in the k position. So it says -5, so this is telling us move down 5 spaces. So every point that we see here already graphed for us, we're going to take it, so we have 1 at the origin, and it's going to go down 5 spaces. 1, 2, 3, 4, 5 on the vertical axis, and everything else follows suit. So 1, 2, 3, 4, 5 here, 1, 2, 3, 4, 5 here, and 1, 2, 3, 4, 5 here. Let me see if I can get this one to go okay. Not too bad. And so that would be the transformed function. We literally just take it and we move it 5 spaces down. Now here, this is a nicer one. I know the picture doesn't look so great, but this is a better one because there's actually 2 transformations here. The a value that we're looking at here as far as our transformation is a -1/2. Well, the negative says reflect it over the x-axis. X-axis, I can't spell. And the 1/2 says, because it's between 0 and 1, that's going to say compress vertically. So we can do this one of 2 ways. We can go ahead and compress it and then reflect it, or reflect it and then compress it. It doesn't really make any difference. But I think it will probably be easier to reflect the points first and then compress it. So you see here, this is the x-axis. That's what we're going to reflect it across. So here, the point at the origin, well, that doesn't change. It's still the origin. So it doesn't reflect horizontally at all. But here, the point that's at +1 and -1, I'm sorry, +1 and +1, well, if I reflect it across the x-axis, that point is now here. The point that's here at 2 and 8, if I reflect it, well, it's not going to really fit on my screen here, but it's going to be down here at 2 and -8. Okay? And same thing here. If I do this one here at -2 and -8, it would reflect up here at -2 and +8, and this one here at -1 and -1 would reflect here. So you can kind of see, even though I don't want to draw it in, but it's going to kind of do one of these kind of things like that. And you can see that's what the shape would look like if we reflect it across the x-axis. Well, now let's compress it. Looking at the parent function, you see from the origin, if I go to the right once, I go up once. Well, now if I reflect it, if I go, or if since I'm compressing it, if I go to the right once, I'm not going to go down once, I'm going to go down half as much. If I go to the right 2 times on the parent function, I go up 8 spaces. Well, we're going to do half of that now because that's what the transformation says to do. So if I go over 2 times, I'm not going to go down 8 whole spaces. I'm going to go down half of that, which is 4 spaces. And we're going to repeat the same process on the other side. Here, if I went to on the parent function, if I go to the left once, I go down 1 whole space. Well, now instead of going to the left once and going up 1 whole space to get to the reflected point, we're only going up half as much. We're going to do it as well here. Instead of going up 8 spaces, I'm only going to go up 4 spaces. So our new functions, our final kind of transformed function, is going to be that blue one right there. So let me clear out the purple one because that one is just there as a guide for reflecting the function rather than the final transformation. And so the final one is what we have there in blue. So by doing the transformation, if we stopped it, it would stop right there. But you know, maybe it's continuous. We could put the arrows on it to show it's continuous. But if it didn't stop, or if it did stop based on what the original points were, the domain and the range would be affected by the transformation. So last one here, last but not least, this is going to incorporate several transformations at the same time. So here, the A transformation, that is a -3. The H transformation is a -2, and the K transformation is a +1. So that -3 says, well, do 2 things. Reflect it and stretch it by a factor of 3. This H value where it says -2, remember the insiders lie, so that says move to the right 2 spaces, and for the +1, that does exactly what we think it means, and that says move up 1 space. Now the reason why I like to have the parent function on the graph when we transform it is because it gives us some points of reference to help us. So you can see we have the vertex here at 0, 0. I have a point here at +1 and another one here at -1 and +1. We would have one at +2 and 4 and -2 and 4, and if we have, and we do have enough room, +3 and 9 and -3 and 9. Those are some good points that we can use to help us do the transformation. Now, there's no, I mean, sometimes it does help to have a specific order in which to transform these things, but we're going to do the translations first. I think that'll work out pretty nicely here. So the true translations are the H and the K value. So I'm going to look at the vertex. That's really kind of like the pivotal point that we want to pay attention to because everything revolves around where the vertex is for this. So the transformations say move to the right 2 spaces and move up 1 space. So here is my new vertex. And let me go ahead and do that in a different color since I did my other points in purple. So there is my new vertex. So we've taken care of both of the horizontal and the vertical translation. Everything else is going to fall into place based on where the vertex is. Well, the vertex says we're going to reflect it across the x-axis. Now the parent function opens up. So if I reflect it across the x-axis, my new one should open down, something like that. And if we stretch it by a factor of 3, that means for every time I go to the left or to the right, I'm going to move down 3 times what I did on the original one. So looking at the original parent function from the vertex, if I go to the right once, I go up once. Well now, from here, from the new vertex, if I go to the right once, I'm not going to go down 1 time, I'm going to go down 3 times, because that's what the translation says to do. It has to be 3 times greater than what it was before. So I'm going to go to the right once and down 1, 2, 3 whole times. And I'll do the exact same thing on the other side. Now, let's try another point. On the original function, if I went to the right 1, 2 times, I would go up 1, 2, 3, 4 times. Well, the translation says it has to be 3 times as large. So instead of going up 4 times, now I'm going to have a vertical shift or a vertical stretch of 12 spaces instead of 4, because 3 times 4 is 12. Now my graph isn't quite big enough for that, but I would go over 1, 2 times and down 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and we would go down 2 more times down to 12, but the graph isn't quite big enough to fit it. And I would do it on the same thing on the other side. So when we graph it, we're going to, oh, and I missed my point, but it's okay. We're going to have something that looks a lot like that, where it's a lot skinnier. And that's what happens a lot of times when we stretch something. If we stretch something, the graph winds up looking kind of skinnier than what it was before. If we compress it, it winds up looking wider than it did before. And so that is how we would take all of the transformations that we would do there. We did all 3 transformations: an A transformation, a horizontal translation, and a vertical translation. So really we had 4 transformations on that one. Now the last thing that it's going to ask you to do is, and I'll explain more in this for those of us that are going to do it in class, but create a function. And I would like you to do it one of 2 ways. Either write a function that has been transformed as an equation and ask a partner to be able to graph it, or graph a transformed function and ask a partner to be able to come up with what the equation would be. What are the transformations? Okay, but that's pretty much it. Understand that this will take a little bit of practice, so we will be talking about it a little more in detail, those of us that are going to work on this in class. And from here, every other transformation that we ever do is going to follow the exact same pattern. So hopefully we can practice a little bit more of these in class, and we'll see you guys soon. So thanks for watching, and I hope you were taking good notes.